Currently, there's over 5,000 AEP line workers in the US and over 5.6 million customers that rely on AEP in the United States. Addressing the safety concerns that field and line workers at AEP face is not only essential for the workers' well-being, but is also necessary to ensure uninterrupted service for those 5.6 million customers. And so, we took on AEP's challenge to create the most accurate AI risk analysis model possible, Hazard LM. There were three main components that went into creating Hazard LM: choosing a large language model, ensuring accuracy and precision, and visualizing results meaningfully. In terms of finding a model, our initial approach involved using Meta's Llama 3.2 local LLM, until we realized all of its flaws. It was resource intensive and super slow as we ran it locally on our machines, and it was way less accurate than the other leading models in the market. In fact, we wrote hundreds of lines of code to fine-tune our model to no avail as it continued to miscategorize our data. But as we tested and compared Llama with other models, we determined that GPT-4o Mini gave us everything that we lacked with Llama, giving us a faster and more precise model.
To clarify, we aren't using OpenAI's public GenAI service ChatGPT, but rather a secure, enterprise-oriented API that employs the GPT-4o Mini LLM. Before switching from Llama to GPT, we ensured that this OpenAI API is compliant with the prevailing security and privacy standards.
For optimally analyzing data with such high stakes involved, we took every step possible to ensure accuracy and reproducibility.
We made sure to cover all aspects of the SCL model and engineered our prompts to adequately focus on human risk and environmental hazards. We also implemented strategic batch processing by executing between 50 to 150 inputs at a time, reducing the risk of it skimming over input values, while also maintaining a decent speed of execution.
After our model was trained, we analyzed our data by assigning 4 attributes to each observation entry. High energy incidence, which tells us whether the observation is high value or not. Priority, which assigns a number representing how relatively dangerous that risk is. SCL category, categorizing the high energy values into the most sweating of the 13 categories. And problem type, categorizing the observation into an overarching general problem that will be easier to solve. These values are then displayed on our website that we built using React and Material UI. Our website has a collection of interactive graphs and sortable tables to visualize high energy incidence. The high energy by incidence graph shows that fall from elevation, electrical contact, suspended load, and mobile equipment are the most frequent high energy incidence categories, suggesting that these areas may require enhanced safety measures. More notably, looking at our incidence over time graph, we can observe trends to determine which categories may need more attention than others.